Hey, he's back.
Valid complaint. It's a bit more expensive though.
Oh,
Yeah, it's
you're
better.
muted, Dr.
You're muted.
Yeah.
I restarted my cable modem and now it's working, as you can see, and all of my devices are working at once. So I guess whatever was going wrong with the modem, the laptop was the first to notice the problem. And then my other devices eventually lost contact. So let me connect my other device so that I can start writing. Continue. Connect audio, start video, share screen. Okay, and let's see. Okay. So if we had an ideal lens, then if we had point object here, every single ray would go to the same place. You might all go there by different paths, but one way or another, they would all get there. And so what we could say is that this is y1, y2 equals minus m y1, where minus m is our magnification. But of course, that's not what actually happens. What actually happens is that we do have aberrations. And so where these rays actually go depends on two things, three variables. It depends on some function of y1, r, how far up on the lens it hits, and an angle. This is a side view. If we were to take a front view of the lens, then there would be this angle phi in there, right? And so rays would, would hit at different angles, and that's going to affect their sideways deflection. And the phi dependence is part of why we see those differently spread out shapes, those not perfect, those asymmetric shapes, either an ellipse, which has mirror symmetry both ways, but is different horizontally than vertically, or a teardrop, which only has mirror symmetry about one direction, okay? But this phi dependence is a big cause of astigmatism and coma. It's a big reason why we have those shapes. So what people did a long time ago was before we had computers that could just trace these, could just use Snell's law at each surface and say, okay, what angle is it hitting at right here? What are the two refractive indices? We'll just solve Snell's law and propagate it. Well, not exactly, because you're always making it discrete, but very, very, very accurately. Before they could do that, people put a lot of work into doing these Taylor series. And I once spent a weekend doing this Taylor series, and I derived like 2 terms from it, and it was not fun. But you could calculate this function as a Taylor series. And one of the terms would be spherical aberration times r cubed, right? You just expand it as a function of r, phi, and y. Another term would be, we'll call it coma times y1 times r squared times cosine of 2 phi. And another term would be our astigmatism term times y1 squared times r times cosine phi. And another one would be called our field curvature times y1 squared times r. And another one would be called distortion times y1 cubed times cosine theta. You might be saying, is that the entire function? No, there's plenty of others, okay? There are other terms that wind up being fifth order and seventh order and so forth. And before people could just run this through a computer, they would do a very detailed calculation of how the exact trajectory of the ray depends on the thickness of the lens, how far off axis. And what this thing I'm calling SA, it's a very complicated term that depends on the radii of curvature of the two sides. It depends on the refractive index. It depends on the thickness. Same thing for the coma. All of these wind up being really ugly terms. That's all they could do, so they did that. And they gave these terms names reflecting the physical phenomena that they give rise to. Looking at this, if we had a perfect lens, what would F be? Well, this function F, not the focal length, but what would this function F be if we had a perfect lens?
0.
0. F would be 0. So the fact that it's non-zero means that our lens is imperfect. Now, if we have an on-axis object, which of these terms would be non-zero?
Y?
Sure, this one will be non-zero, but which of the other ones will be wait, no, wait, actually, Y will not. On-axis object? Is Y non-zero for an on-axis object?
No.
No, Y is 0 for an on-axis object. So if we have an on-axis object, this is the only non-zero term. And this is why spherical aberration is important, because even there are a lot of applications where you're only looking at things very close to the axis. All right, if you think about a microscope, the focal length of a microscope lens might be a millimeter, okay? A couple millimeters, depending on the situation. Your field of view might be 10 microns. So you're only looking at things that are no more than 10 microns from the optic axis. And yet, that's only 1% of the focal length, okay? So in the grand scheme of things, if you were looking at, you're in a microscope, spherical aberration, it's not the only thing, but it would be the dominant thing, because Y would be tiny for most of the things you're looking at with a microscope, whereas R could be huge. Now, as you get further off axis, coma starts to matter. And by the way, there are analogies to this for telescopes where the objects are effectively infinitely far away. Then you write everything as a function not of Y, but of the off-axis angle. And again, with a telescope, modern telescopes, the off-axis angles are usually quite tiny. They're pointing, at least astronomical research telescopes. Maybe it's different for a telescope used more like field binoculars or something. But for an astronomical research telescope, the off-axis angle will be minuscule. So spherical aberration, it's not the only thing they worry about, but it will still be the #1 thing that they worry about. As you go further off axis, well, now y is non-zero. Of course, y squared is non-zero, and y cubed is non-zero. If I take a tiny number y, and I square it, what's bigger, y or y squared?
Why?
Exactly. So this is the next most important thing. And then astigmatism and field curvature are the third most important things. Now for cameras, it could be a different matter. If you're, say, a photographer, unless you're doing very long distance wildlife photography through a telephoto lens, then you're looking at things, maybe you're not even doing extreme close-ups. Artistic photographers often do extreme close-ups. But just, a photographer for a newspaper, a wedding photographer, whatever, you're looking at some pretty big angles. For them, distortion matters, field curvature matters, astigmatism matters, spherical aberration, not usually as important. Coma, not more important than spherical aberration, not as important as astigmatism. So what I want you to take away is that I described several physical effects. I showed you spherical aberration. It's that a point object on axis turns into a circle. And I said that it's a result of the shape being wrong. Coma produces a teardrop shape, astigmatism produces ellipses, and so forth. What I want you to take away is that they arise from distinct mechanisms, and which ones dominate depends on whether you're very close to the axis or very far from the axis. Close to the axis, spherical aberration dominates. Far from the axis, astigmatism and field curvature and distortion will dominate. Any questions so far?
So aberrations are always happening, right? Except we've gotten good at making lens to where we minimize its effects.
Aberrations are always there. You can make the effects small. Basically, not that lens designers do it this way in practice, but basically what they're trying to do is they're trying to make these coefficients small. You could think about picking some combination of lenses so that all of these effects wind up being small, so that these coefficients are small. Each of these coefficients would depend on all of the refractive indices, so all the n values, all of the curvatures, thicknesses, and spacings. All of these coefficients could be, the more lenses you add, the more elaborate those expressions are. They could fill an entire page. I produced a very long Mathematica file just trying to calculate the spherical aberration and coma coefficients for a fairly thin lens. They would be expressions that depend on all of these variables, and you're trying to pick the combination of variables that makes these coefficients as small as possible, right? Before they had computers, some people would actually do that. They derive a formula for the coefficient of r cubed, and another formula for the coefficient of y1 r squared, and another formula for the coefficient of y1 squared r. And then they would say what combination of curvatures and indices and whatnot will make these coefficients, if not zero, at least small. Does that answer your question?
Yes, thank you very much.
Okay. Go ahead.
And is Zmax doing that or are we going to get into that? Is it doing it in the quick focus function, or we're going to get into that with the merit function, I guess?
in both the quick focus and the merit function, what Zmax does is it just traces the rays and evaluates the image quality. And it says to itself, okay, if I change this curvature, how does the image quality change? Does it get better or worse? And then it tries changing another curvature and says, how does the image quality change now? Now, Zmax is not magic. A human being cannot just go to Zmax and give it something with several thicknesses and several curvatures and spacings and be like, okay, computer, do it. Because let's say the computer was going to try a dozen values of this curvature and a dozen values of the next curvature and a dozen values of the next one. That's 12 times 12 times 12. Okay, that's like 1,700. Well, a computer can deal with 1,700 tries, except that each of those tries will take some time, but still it can do it. But then you throw in another variable. You multiply it by another dozen. Every variable you add in is increasing the complexity of the calculation exponentially. And it would not, like that fancy lens I showed you earlier, if you just told Zmax, go do that for me, it would take the age of the universe to do it, even on the best computer in the basement of the NSA. Because the sheer number of variables would be impossible. So a human being cannot just say to a computer, hey, do it for me. Not just because of what I always say, that if we start letting the computers think for us, we're in trouble, but because some of these problems require so many variables that the brute force approach will take until the end of the universe. Despite everything I've been saying about, well, because of what I just said now, and despite what I was saying earlier, I'm going to give you one calculation that people still do. Because this calculation, it's not that we take this calculation, do it, and declare our job done, but the insight from it, the intuition we get from it is a good starting point. People found the following design rule. If we've got a lens with radii R1 and R2 to image something from a distance S1 to S2, it turns out when you do the algebra, this is the easiest way to write the answer. Yes, the n is the refractive index of glass. All right. The rule is this. People found in the 19th century that if this is satisfied, okay, if this equation is satisfied, then the spherical aberration coefficient is minimized. Well, why should we care about that, or what can we think from that? Well, let's start talking about a few different cases. Let's say that R2 equals negative R1. This thing on the left is called a shape factor. All right. And if R2 equals negative R1, then our lenses are symmetric. Our lens is symmetric. And our shape factor, the shape factor is sometimes called sigma. Sigma equals 0. Well, sigma equals 0, then S2 minus S1 is 0. So 1-to-1 imaging has a symmetric lens. And sometimes people need a 1-to-1 relay lens. Sometimes they just need to extend the beam path a little bit farther Maybe because they have to put a detector further out than they anticipated. There are some other constraints in some sort of benchtop design. Maybe because they want to put a few more filters and other things that are doing things to the spectrum of the light, but not to the actual direction that the light is traveling. So if they want to do things to the spectrum or intensity of the light, but not do anything to the direction that the light is traveling, the one way to buy beam path is just with a one-to-one relay. Okay. Let's do case 2, right? Let's say S2 is much bigger than S1. All right, so that would be in the case of magnifying. S2 is bigger than S1. Is sigma going to be positive or negative? Let's vote on it. Just put plus or minus into the chat. Everyone's saying positive. Let's see here. S2 is bigger than S1, so this is positive. Assuming n is bigger than 1, which is true for normal materials, then this is positive, but that is negative. Okay, so sigma is negative. Now let's think about the lens shape that we're going to have. We're going to have, oops. So we're going to have an object here, an image here, and the lens is going to be somewhere there. All right, now if it's bulging outward, then if R2 is negative, yeah. Okay, let's just try different things. Let's just start by guessing R1 is positive, okay? If we guess that R1 is positive, then in order to have sigma be negative, let's see here, if this was bulging outward as well, if it was bulging outward by more, sigma is R2 plus R1 over R2 minus R1. If I had this bulging out even more, everything very exaggerated, you tell me, what has a larger magnitude, R1 or R2? Now, obviously R2 is negative, so R1 is strictly speaking larger than R2, but what has the larger magnitude, R1 or R2? R1 is kind of flat, R2 is very curved. So which one has the larger size? Which one is the larger magnitude, the larger absolute value, R1 or R2?
R1.
Yep, because R1 looks like it's cut out of something nearly flat like the Earth, whereas R2 looks like it's cut out of a small sphere. It's only on small spheres that you notice the curvature. So what we would have is a small negative number plus a large, okay, the top is plus. The bottom, we'd have minus, minus. All right, we'd be subtracting. So this would work, okay? And what this would mean is that they hit the surface like this. They get deflected a little bit, and then they get deflected more there. I didn't draw it to scale. But the idea is that by hitting the rays that are coming out at the largest angle, hit a flat surface so that they won't, they hit a flat surface, all right? Or an almost flat surface. Now, if I made R1 large and negative, I can make R2 small and negative. If I did something like that, then let's see here. R1 large and negative, so our top would be negative. We would have a small negative minus a large negative. That could also work. What we would have then is a situation like this. So the rays would be hitting in a way that they're still not hitting it normal, but we'd have a small angle. Then they would come in and they would hit the next surface, if I had drawn it more reasonably, at a smaller angle than they would have otherwise. So what I want you to take away is that when the shape factor is negative, the overall bulge is to the right. Basically, the bulge goes towards the more distant object. Any questions? No questions at all? Then I've thrown a lot at you. I'm not going to try to start merit functions today, but I do want to give you some intuition for this. I want to at least verify something that we said earlier. I thought I had CMAX, there's optics. All right, I want to at least verify something that I started saying about third order aberration theory. I want to give you a qualitative view of what you're going to essentially be proving rigorously on Tuesday's assignment. And then on Monday, we'll talk about merit functions. Sorry, that's my default file. Let me decide to restart everything. Okay, let's just see what happens. We've got a pretty good lens. We've got a fairly small on-axis spot size, all right? We're looking at spherical aberration. So the on-axis object is forming something with a radius of 20. Now, if the spot size, if we have spherical aberration, what should happen to the spot size when I double the aperture? what should the spot size get multiplied by if it's spherical aberration? On-axis object, how does the spot size depend on R? How does it depend on Y? Come on, we just talked about it a few minutes ago. Did you take notes?
Wait, Professor, can you repeat the question again?
On-axis object, spot size, how far off axis the rays arrive. So think about the spot size as how far off axis the rays are going. You know, ideally, if we have an on-axis object, all the rays will come together right on axis. So all of the rays will be exactly there, not above it or below it. But in practice, we know that they do come to a focus somewhat off axis. So how does the position where the rays could go depend on R, and how does it depend on Y? Look at that Taylor series. Look in your notes at the Taylor series. Depends on R cubed. Yes. If the object is on axis, then the place where the rays go to is proportional to R cubed off axis. So if I double the aperture, I'm doubling R. What should happen to the rays? What should happen to the spot size? Excuse me. Eight times as big. Yeah. And so it actually got even bigger than that, which tells us, but we didn't focus it. Let's focus it. Hey, we focused it and we got 163. We went from 20 to 163. Which is almost exactly 8 times 20. It was actually 20 point something. 8 times 20 point something is going to be a little bit more than 160. So this is pretty much perfect. On the other hand, what we notice is that let's look at this off-axis object. Here the spot size is 1300. Let's have it. And we go down to 480. Now we could do a quick focus. And the off-axis object actually got worse. Why do you think that is?
I mean, are they weighted the same? You just focused on the on-axis object, right?
Yeah, the off-axis object got absolutely no weight whatsoever. Let's move the off-axis object closer. All right, let's move it closer and let's give it all of the weight. So it now has weight 1 and the other one will give weight 0. And we'll do a quick focus. Okay, yeah, that is a really weird coma case right there is what that is. So spot size of 30. Then I double my aperture. And I focus. And the spot size goes from 30 to 180. So it got multiplied by 6, which is more than 2 squared, but less than 2 cubed, which means that we have a combination of spherical aberration and coma here. So to get actual detailed predictions from this theory would require a much more elaborate analysis by hand than we want to do. And in the end, what we really want to know is, where do the rays go? And Zmax tells us that.
Sorry, for the spherical aberration, it's based on r cubed. And I know it's not based on y for on axis, but for off axis it is, right? You would multiply it by how far off axis it is.
It's not that. Think of spherical aberration as spot size depends on y. Spot size of course depends on y. You technically, right? The spot size changes as y changes. There's one term, and only one term, that doesn't change as y changes, and that's the one proportional to r cubed. And they just call the effects of that term spherical aberration. Qualitatively, aberration is, well, we have a spot that didn't form, we have a point object that didn't form an infinitely tiny spot. That's qualitatively what aberrations are. So qualitatively, all aberrations are aberrations. And they all are kind of like spherical aberration because they all involve the thing having the wrong shape. But quantitatively, you've just got this Taylor series with many, many terms. And the first several terms are the ones that are third order. You notice in all of those terms, if I go back to my other device, I had r cubed, y times r squared, y squared times r, y squared times r, y cubed. In all of those, the sum of the powers was 3. Now, if we kept going with the Taylor series, we could get an r to the 5th term, we could get a y times r to the 4th term, and a y squared times r cubed, and so forth. And in the 19th century, people worked on that, and even in the first part of the 20th century. But as soon as they started getting computers, people were desperate to get away from that. Can anybody guess as to why it is that I said, well, we've got third order aberrations, but we don't have second order? And I talked about 5th order, but I didn't mention any 4th order.
Do even order terms cancel out somehow?
Even order terms do go away. And there's a physical reason why even order terms really shouldn't be there. If I have an object that, I'll just redraw it. Right? If I've got an object that's above the axis, the image had better form below the axis. All right, so all the rays had better have y1 is positive, y2 had better be negative. Now, if I flip everything, if I suddenly go like this, and I don't just flip the object position, but I'll draw some rays, okay? Then this ray, maybe the ideal image would have been here. And in the other case, the ideal image would have been, oops. There, I didn't draw it, didn't draw it carefully, symmetrically. The ideal image would have been like that. If I flip everything around, y had better flip. If I flip every single variable, y had better change. You know what? I'm going to make this nice. We got just a few minutes. I'll make it nice. All right, that was 2.5. This will be 2.5. All right, if I flip everything, then I had better, if I flip absolutely everything, then Y had better flip. All right, that's the rule. And likewise for the other rays. So if I flip everything, then Y had better flip. The only way to make sure that if I flip everything is that the powers had better add up to an odd number, all right? Maybe, if I got an R squared, well, R squared won't change, fine, but then R squared had better be multiplied by Y. I might have a Y cubed, that's fine. Then Y cubed had better either not be multiplied by anything involving R or be multiplied by R squared or R to the fourth. If I had Y cubed R and I flip everything, well, suddenly Y cubed becomes minus Y cubed and R becomes minus R, and their product doesn't change, and that's a problem. All right, that's all I'm going to talk about. I will stick around if people have questions about the project due next week, but I think we went through most of the concepts here. And then on Monday, we will talk a little more about aberrations. We'll do merit functions, and then we'll talk about lenses underwater. Have a good day.
Thank you.
You're welcome. Julian, do you have a question?
No, sorry, I was just setting up my mouse to exit the call.
No
Thank you.
problem. You're welcome.